We are reaching to the last session in kinematic analysis of robotic manipulators, and in this session we will discuss about inverse kinematic of general 6R manipulator or 6 degree of freedom manipulator. As we mentioned in the last session, there is a theorem given by Pieper, which we call Pieper solution, when 3 axes of a 6R manipulator is intersecting, then we can decompose the position and orientation inverse problem into 2 separate problems, and then we can solve them quite easily. As we mentioned it before, consider that the origin of the last 3 coordinate system, or 4, 5, and 6 coordinate system, are intersecting at one point. We call that point the wrist point, and then we find the position of the wrist point from the coordinate system, and the orientation of the wrist from the last 3 coordinate system. By separating these 2 problems into 2 consecutive problems, we can solve them quite easily. Of course, not very easy, but it is much easier than solving all 6 equations altogether. As you see in here, using, for example, Denavit-Hartenberger convention or Paul convention, in Paul or in Cray convention, we can find the position of the wrist point, we call it O4 here, as a 3 consecutive homogeneous transformation, and the last link that for a general case, this last link has a position and orientation like this, a position like this, and then we can use this position, this transformation into a formulation like this. So we have 3 parameters here, theta 1, theta 2, theta 3 usually as the variables to be found, and this is given, so we can just multiply these 3 together in a general and the most general form for a most general link decomposition. We have a problem like that, G1 and G2 and G3 are given here. All this G1, G2, G3, as you see, is this function. This problem is a function of theta 1 only. G1, G2, and G3 are the function of theta 2 and F1, F2, and F3, which F3 is a function of theta 3 as well, and the parameter of the system. So by this terms of variable decomposition, we have theta 1, theta 2, and theta 3 variables all together. Of course, it is quite nonlinear and sophisticated equation for a general manipulator, but in a specific manipulator, many of these parameters might be the cosine of alpha might be 0 or pi over 2, the alpha, and then many of these terms may be simplifies. Now, if we solve for this 3 equation, now we can consider only the magnitude of PO4 with respect to 0 as R, as what we did in a simple 3R manipulator. So we have G1, G2, G3 point. We can say that, okay, R, which is G1 squared plus G2 squared plus G3 squared, can be found, and as we manipulate these 3 substitution, we reach to this point, and this point can be written in this 2 equation. This R can be written as a function of theta 2 plus K3, which K3 is rather a long equation, and the Z component of that the Z component of that, which is G3, is quite easily found as function of S2 plus K4, which K4 is also a function of alpha 1 and F3. Now here we can eliminate theta 1 quite easily from especially from the Z2, from the second equation here. If different cases available here, we can see, for example, that let me just change the role of the newcomers as the presenters to have everyone. Now, if alpha 1 is equal to 0, then this equation is R is equal to K3. K3 is a function of F1 to F3, only a function of theta 3. We can solve for that. If sine of alpha is equal to 0, then this equation is 0, and the Z2 is equal to K4. K4 is a function of F3, a much simpler equation of F3, and we can again solve for theta 3. And if it is not the case, if none of these two parameters are equal to 0, then we have two equations, and we can use some sort of elimination here to find to eliminate S2 and C2 from these two equations by just simply adding the summation of the squared of these two equations. If the summation of these two equations, it becomes a larger, more sophisticated equation, but only a function of K3, K1, K2, K3, K4, which, as you see, is a function of theta 3 only. In any case, in simple case, or in the most general case, we can find the theta 3 from this equation. We will show it in the next example. And since having theta 3, then we can solve for theta 2 and theta 1. How we can solve for theta 2 and theta 1? Go back to these two equations. As you see here, we have a function of theta 1 and G1. If we have found basically the theta 3 formulation, then we can use this equation to find only as a function of theta 2, find the function of theta 2, and these two equations, which are a function of theta 1, we can find a function of theta 1. Consequently, from theta 3, 2, and theta 1, one by one equation. Now, three of the parameters are found from the position of point 0.04. And three parameters are remaining, or three joint variables are remaining, which are the orientation variable. The orientation variable can be solved with the three other homogeneous transformation. These three homogeneous transformation, which are a function of theta 4, 5, and 6, all of them are intersecting to each other, provide us a full orientation. We can usually find that orientation from R6 to 1, the goal for orientation of the final orientation, which should be given to us. From that, we find the inverse of 4 to 1, just considering theta 4 is equal to 0, and then we find a very simple rotation matrix, which can be usually written in terms of Euler angles, usually Z by Z angles, and that equation can be solved one by one. How it is solved, we'll show it in the next example as we go forward. So Pierre in his theorem showed that if we have intersecting point at the wrist, the inverse kinematic problem can be solved quite easily. Any case, let me go through a specific. This is the general way to find the solution. Now go to a real solution, a real one solution. Just to give a break here, your second assignment will be uploaded today. We don't give you pay ke shadi like what you have usually in high school or in elementary school. We give you some 3 days of vacation. So from this is the last week of our classes before the new year, and we have 2 weeks holidays. I'm saying this to Hussein, which is not Iranian and maybe not New Year holidays. We have 2 weeks of holidays, hopefully within the semester, so you have some time to get some rest and also do a bit of work on this. I put the assignment due just 1 week after the holidays, in the 3rd week of Farvardin. So you have quite enough time to reach to the point that we are teaching up to here, and also do the assignment. Regarding the project and the assignment, we will follow a number of specific robots in assignment and in the project. And this will be given to you, the first part of this will be given to you as your first assignment and the first part of the project. They are quite similar to each other. In the assignment, we give you 2 simpler robotic manipulator with 3 degrees of freedom or 2 degrees of freedom manipulator that you should find the Denavit-Hartenberg forward kinematic, inverse kinematic solution. And for your project, we decided to give you a simplified version of surgical robot, which will be used in Da Vinci as well as in Precise and in similar to what we are using in our haptic system for eye training system. So it is a real, of course, a part of the real manipulator. To make it simple, it is a real robot with 3 degrees of freedom and a parallelogram architecture. And this is very, very important. This is a very interesting idea to have a parallelogram structure in the robotic manipulator. You will get familiar to it and you will work on the kinematic solution, and furthermore we will go, as the course goes along, we go to the Jacobian dynamic and control of the same robot in a consecutive term. So usually we distribute the term project into the course, that you have more freedom to work on it, not on a just at the end of the semester, but during the semester as we go along with the course. Why I mentioned that here, this is because of what we see in this example. This example is a 6 degree of freedom FANUC manipulator, industrial manipulator made by FANUC. This is basically very, very interesting architecture. Many industrial robots have similar construction here, and as you see, there is this is the main length of the robot, and you see a parallelogram or something added here to this robot. We are usually having such a extra link to the robot. This is generally used because of a mechanical idea, a very interesting mechanical idea, that if we have a parallelogram architecture, as you see here, we have a parallelogram, and to move the base, you can put the motor right on the base, so you don't move the motor, the base motor, when the robot is moving. As you go further, for the first joint, you have a motor here. For the second joint, which is in here, you can use the parallelogram, and instead of bringing the motor on top of the robot, you can using the motor on the bottom at this point, that another, or even at this point, you can just simply have a symmetric point here. By this means, the very heavily weighted motors of the robot is coming down to the base to reduce the moving weight and inertia of the robot to make it much more effective in terms of manipulation. And as well, you can see there is something here which is a weight compensators. This is usually in a FANUC or in many robotic manipulator, you have a hydropneumatic weight compensation here. I am not going through the mechanical design, but these are usually basic ideas being used here, and that's why we can use such design. We can see such design very commonly in many industrial robots, usually the industrial robot that goes back to 10 years ago. And again, we have the Pieper solution here. The wrist here are three intersecting joint here. I will show you the details in the next slide, but we have the Pieper solution as well. So we have two items here. First item is that we have a 6 degree of freedom, as we see, 6R manipulator. The first 3R manipulator, this is a rotating base plus a parallelogram structure, or to use the second link. And to move the second link, instead of putting a motor here, we can put a motor here. And just to move these motors, instead of putting the motor here, we can go back and use the motor somehow. And the old design is such that we have less moving weight in the manipulators. And this parallelogram, this structure is given in your first assignment. Again, as I mentioned here, we have a parallelogram structure in the first 3 degrees of freedom, and we have an intersecting 3 intersecting joints at the wrist. So this is very, very common in many industrial robots, and now we can solve the inverse kinematic problem of that. Of course, we should first work on the forward kinematic, and then go to the inverse kinematic. This is a 6R manipulator, so we have 6 theta 1 to theta 6 as the unknown variable for inverse kinematic, and we have the position and orientation of the end point, which is the point that the end effector is reaching to here, up to here. Considering that into mind, we can use the David-Hartenberg problem, as we mentioned here, with Paul convention. We can find theta 1 and Z0, as you see here, and Z1, and then we have Z2, Z3, Z4, and go ahead for that. And these 3 intersecting points, Z4, Z5, and Z6, as you see, are all intersecting at this point, which we call it wrist, and we consider it as the P point. And we have an end effector point, maybe here or somewhere, maybe a tool we have on top of that, any point here which has the 6 structure, the difference from this point. We can find the David-Hartenberg problem by Paul convention quite easily. I don't go through the forward kinematic. We have done that for many examples. And as you see, there is no matter if we are using this parallelogram here, since in the problem, this parallelogram is not making that much difference. The only thing is the location of the motors are, as you see, we have two motors here instead of having one motor here and one motor here, and we have this link parallel to this link. So when we move this link, we can move this link, which this link is actually the third link here, and this link is parallel to this one. So by moving this one, we can move this. We can use the weight compensation as you see in here in the mechanical structure of that. But in terms of kinematic structure, we have this frame assignment here, and we can basically find the Denavit-Hartenberg homogeneous transformation as theta 1, theta 2, theta 3, very simple with this, and theta 4, 5, and 6 here. We have some D4 and D6 here, as you see. We have D4 and D6 as some links, and A1 and 2, A3 as the first three length of the links, and all the D3, A4 to A6 is equal to 0 because we have intersecting ribs by this means. Anyways, by this means we have this 6 transformation given here, and we can give the final solution, what it is given. The end effector point Q, Qx, Qy, Qz is given, and also its orientation. The orientation is given with a rotation matrix. So this is given basically in inverse kinematic problem, which we call it with U, V, W, 3 columns to make them much easier to interpret in the system. So this is given, and we would like to find these 6 parameters, these joint variables as the inverse problem variables. Now, to do that, we do the same, exactly the same paper approach, but now we can go one by one quite easily, and I would like you to follow me how I treat the problem, and then after the class do it yourself one by one, not looking at the solution, try to work it out by yourself. So we see that we have an end effector and we have a wrist point. The wrist is where exactly these 3 points are, these 3 axes are intersecting. We call it P or W, and we consider that P point to separate the orientation and the position. This P point, as you see here, Px, Py, Pz, can be very simply defined from the Q point. If Q is given, since in the problem the point Q is given, not the wrist. But the wrist and the position has only a D6 and some orientation differences. So if we have Qx, Qy, Qz, we have the position here, and we have the orientation of the end effector, which are given by Wx, Wy, Wz. Only the last orientation is important, which is the orientation which we have along the Z6. If this is the case, we can find the Px, Py, Pz quite easily from the given Qx, Qy, Qz and the orientation, plus the D6 parameter, which is the length of from the wrist point to the end effector point or to the tool point, we call it D6. So this is given, so this 3 Px, Py, Pz is given. Now we have this position. We would like to find the first 3 thetas, theta 1, theta 2, theta 3, as we discussed in the previous section. So if you look at this, you can see that if we have the P, now look, go back into this point, we have the position, consider that instead of given the orientation and position of Q, the position of P is given. We have found it easily from this point. Now if you look at this, we have two important aspects here. We use it one by one. I don't say both of them here, I just say the first one here and use that. If you have the point P here, and considering it in the frame 3, if the vector P is given to you, P can be given in the frame 0 or in the frame 1 or 2 or 3. If considering only the frame 3, as you see here, we have x3 here, and we have this z2 here, and we have x3, z3, as you see along here, x, y, and z. So we have x3 and z3 here, and this point P. This point P in frame 3 has a length of this link length, which we call it A3, along the Z direction. Or we call it D4, sorry, we don't call it A3, we call it D4. Here, from here to here, it is D4. So, as you see here, we can easily see that P, the vector P in frame 3, can be given by these three vectors, and this makes the life much easier, since we have this given in D4. Consider that we have this from the end effector. Now we are coming from the base to here, and then we would like to make these two equivalent and find the inverse solution. Now, if you have this given in the third frame, you can easily find it in the 0 frame by multiplying it to the similarity, the homogeneous transformation, A3 or T3 with respect to 0, or A3 with respect to 0, which is A0 to 1, 1 to 2, 2 to 3, and which we have given it here. These three consecutive terms, which is only a function of theta 1, theta 2, and theta 3. But making it a bit more smarter, instead of manipulating all these three together, we can keep one of them out. We can bring A1 to 0 inverse to the other side of the equation. Now, this is quite easy, and we use this one to make the equation a bit simpler with respect to theta 1, theta 2, and theta 3. Now we have A1 to 2, A2 to 3. We need only to multiply these two together and find the inverse of this. We have worked on finding the inverse of this matrix. It's very simple. You just transpose the rotation matrix and use the minus R transpose to this part as the position matrix. Now, if you look at this, you find this, and you find this manipulation, you have somehow separated. The theta 1 comes in the left-hand side of this equation, and P0, as you see in here, P3 is also very simple, 0, 0, D4, so it makes it much easier. You have only D4 here. In the left-hand side, you have a function of theta 1, and in the right-hand side, you have the function of theta 2 and theta 3. Again, still the problem is quite complicated, but we have make it 2 times simpler. And we know that Px, Py, Pz is given, so from here we have this one, and we would like to find theta 3. And as you see, this equation is only a function of theta 1. this one is a function of theta 1, theta 2, theta 3, but because of the structure that we are using here, this is a simple equation of theta 1. So we can find the theta 1 just from this angle. We have the sine and the cosine here. You can find theta 1, as you see, just the tangent of the theta 1 is py over px, and you can find the arctangent from this equation. Of course, you can also use the half tangent equation to bring this into a second order equation and find the solution, but here it is easier, and it doesn't really need to do further manipulation. Just by having this trick, which is a very important trick, to separate it to it, and the structure of and the Navier-Hartenberg problem that we have in this specific robot, this equation is much easier and this is found. We have theta 1 and we have 2 angle for theta 1. We have 2 solutions. We have py over px. If we have arctangent, it gives us only 1 solution. But since we are using only tangent, so you can find 2 joint angles for this between 0 to pi over 2, and we can have the inverse in the second and in the third and fourth quadrant as well. So here we have 2 solutions for a given px and py, but now since the theta 1 is given, now we can work on the theta 2 and theta 3. Now you can also use the mechanical structure, the second important thing, to find the theta 2 and theta 3, or somehow eliminate some problem here. You can see that as you see this point, the first one was very easy, that P1 with respect to x3 is d4 only in the direction of z4. This makes our life much easier to find the theta 1. The second thing that is important is that if you look at the radius or the distance of z1 with respect to the 0 frame, this vector, the vector of z4 from here, this really is not dependent on the base rotation. So if you change the base rotation, this length or this radius is not changing. This radius is only changing by theta 2 and theta 3, the angle that we open our hand. And the rotation really doesn't give the difference in terms of the radius of the Z point Z in here. What does this giving you in mathematically? You can find this Z by square sum of these 2 equations. So we go to these 2 equations now, 281 and 282, and then we can use the sum of the squares of this problem. Now if you just make them squared and add them up, if you see, you have sine of theta 2 here and cosine of theta 2 here. If you add the sum of them, the theta 2 will be somehow released. And the same thing with the theta 3. Of course, this is a bit much harder. If you do the sum, if you just eliminate this, the distance of between A and P is independent of theta 1 and theta 2. So you can just simply eliminate theta 2 as well here. By just using the sum of the squares in here, using the sum of the squares here, we have px, py at theta 1 given. So this part, the left-hand side is all known variables. The right-hand side, by summing up and squaring, the theta 2 is will be eliminated, and we have an equation in terms of only theta 3, which we call it kappa theta 3, sine of theta 3, kappa 2, cosine of theta 3 is equal to kappa 3. Of course, kappa 1, kappa 2, kappa 3 is a long equation, but from all of them are known. Kappa 1 is this, kappa 2 is this, and kappa 3 is a very, very long equation. Now we have an equation only as a function of theta 3. And this can be also, this is not equal to 0. If it was equal to 0, we could easily use a arctangent here. This is not equal to 0. This is equal to a non-zero variable. And we can use a half tangent relation, as I mentioned in the last session. To theta 3, we can use a half tangent to give a variable t3 or a u3. And to equate this or to equalize this to a second order equation in terms of theta 3, and theta 3 can be found very easily. Two solutions of that can be found very easily by this equation. And this is solution of kappa 1 square plus kappa 2 square minus kappa 3 square is positive, and if it is negative, there is no solution. And if it is 0, it would be much more interesting. We have the two double solution, as I mentioned. We will talk about that later in the next session very much. Just remember this singular point, the case where we have 0 solution here is very, very interesting. What does it mean when we have two? We can easily find this tangent of half angle very easily by the solution of the second order polynomial here with two equations. These two solutions give us like elbow up and elbow down, like a 3-arm manipulator, two solution, two valid solution here. So basically we have two solutions for theta 1, two solutions for theta 3, making it up together, we have 4 solution for these two examples, if there is a solution exists, or the point is in within the workspace of the robot. So we have the theta 1 here, theta 3 here. Now we can easily find theta 2. Theta 2 can be found by this equation. If we have the theta 3 and theta 2, we can find the theta 2 equation. Now going back to this 2 equation, we use all the known variables all together to the right hand side and the rest in the left hand side. We have a variable of theta 2 here, only theta 2 here, and gamma 1 and gamma 2. Of course, again, these parameters are very long. We use a shorthand parameters as you see here. They depend on theta 3, theta 1, px, py, pz, a lot of parameters which has been already found in the previous solution. We have 2 equations from sinus and cosine, and then we can use the tan2 variable here. From here we can find the cosine and the sine. This is a linear equation with 2 unknown sine and cosine. Then you can find the inverse of this matrix, mu1, v1, mu2, v2, and use the tan2 equation by just simply sinus, giving the sign of sine of theta 2 and cosine of theta 2. One unique solution will be found. 4 solutions we have before, and we have actually 4 solutions. It can be shown that from these 4 solutions, 2 of them are not feasible with the structure of the robot. Since the robot is somehow here and they cannot go back, we have still, because of the limitation of the motion limitation that we have, 2 of these solutions are physically possible. Mathematically, we have 4 solutions, but physically we have 2 solutions found from this equation. Now we have find theta 1, theta 2, theta 3. The problem is not solved yet. Half of it is solved. The most difficult part is solved. We have found the position of the wrist. From this first three equation, we should find the orientation by the next three equation. And if we go to the last part, now let me also complete it, then we can have some more discussion with you, and if there is any question here. We can now find from p-pair solution, we can find the orientation. Exactly the same way that the p-pair has said, so that if we have the solution, we have the orientation and the vector orientation quite easily. Let's go back to see what we are talking. We have this R 6 to 0 from the problem, from the inverse kinematic problem. Consider that UVW is quite given. Now we would like to find theta 4, theta 5, and theta 6. This is given, and we would like to find this. Since we have theta 1, theta 2, theta 3, we have a 3 to 0 quite easily. We can multiply that, we can find the inverse of that, and giving it to this, we can find a 6 to 3. A 6 to 3, as you see, a 6 to 3 is the manipulation of a 4 to 3, 5 to 4, and 6 to 5. We have three unknown parameters, theta 4, theta 5, theta 6. By multiplication of these three equations, as you see here, we have this three equation. This by multiplication of these three and using symbolic MATLAB toolbox, you can find simply this equation from one side. From the other side, a 0 to 3 is also very given to this, and you can find the inverse of this manipulator as well. So you have this one, you have also this one. This is unknown, this is known. If you just multiply these two together, it gives you a very long, basically 12 parameters in a matrix form, or 12 equations from this matrix form. And you should just ask God that from these 12 equations, some of the equations are not very complicated, and we can work with that. And you can find that if you multiply these three together, you see that, oh, very good, this is very simple. Cosine of theta 5 is without any parameter multiplied by. Of course, this equation is very hard. We have 4, 3, 4, 5, 6, 4, 5, 6 theta all together. But this one is simple. This 2 is also simple, and these two are also simple. The same way we use the inverse Euler parameters, we use the same thing in here. We are using this part of equation as our solution. So theta 5 is given here. At this point, we multiply these two together, two known parameters, and look at the R33, the 33 component of this equation. Whatever it is, how long it is no matter, because everything is known there. Consider that this then is given, we can find the cosine of theta 5 easily from here. And it can be manipulation. You can see that R33 is a function of theta 1, theta 2, 3, Wx, Wy, and Wz by this manipulation. So theta 5 could be found here, and cosine give you two solutions again. Here up to here we have 4 solutions. 2 of them were practical. Now in terms of the orientation, again we have 2 solutions here as well. And given theta 4, then we can go for theta 5, we can go for theta 4, and from these 2 equations, and theta 6 from these 2 equations, we can find these two quite easily in the next session. So using component 1, 3, and 2, 3 component, 1, 3, and 2, 3 component, we have sine of theta and cosine of theta times theta 4 given multiplied by sine of theta 5. So you can just simply, if sine of theta 5 is not 0, then you can use this solution to find S theta by tan 2. And the same thing we can go for the component 3, 1. These two components, you have sine of theta 5, cosine of theta 6, and sine of theta 6. So you have two parameters. You can go to using the tan 2 for theta 6. And what if sine of theta 5 is 0? Then, as we thought before, these equations are not working. If sine of theta 5 is equal to 0, then cosine is equal to 1. These two equations becomes much simpler, and we can find the difference between theta 4 and theta 6. This is the singular point and the regenerative the problem that we have in our Euler angle inverse solution. We have the same problem in here. But the solution is complete now. We have all 6 joint parameters with a very long journey of dividing the solution and finding one by one all together. Now, if there is any question, please. Now it's time to have your question and the discussion toward the course.
Actually, why is for the solution?
We don't have your voice quite clear. Can you again tell us?
I'm saying why 2 solutions of tan 2 were not practical.
Not tan 2. tan 2 gives you one solution, basically. Because tan 2 is a 4-quadrant inverse solution. So if the sine of theta 4 and cosine of theta 4, if the sine of these two variables, the sine of them are given, if they are positive, if both of them are positive, these are in the first quadrant. If both of them are negative, they are in the third quadrant, and so forth. So there is no 2 solution. For tan 2, we have only one solution. We have to...
Sorry. I don't know if it was the previous slide or the other one, but after the tan 2 equation, it was like 4 solutions that 2 of them were not practical, I think, at that point.
Okay. This is not mathematically found. We have 4 solutions mathematically, but look at the robot itself. The robot has some motion restriction. So suppose that if you plot the data, the 4 solution for any cases, you can see that these angles cannot be, let's say, the angle of this joint cannot be minus 180 degrees. One of the solution goes to that part of the problem, which is not practical. If we don't have any limitation in the motion, we could have a different solution. But as you see here, we have some, since we have a parallelogram here, we cannot move the robot more than plus minus, let's say, 60 degree or 90 degree. That's why the other solution is out of the limited theta that we can add to the system.
Thank you. By the way, I have a lot of delay, so I really can't track the movement of cursor. If any equation has numbers, could you please also refer to their numbers as well?
Okay, sure.
Thank you so much.
Thank you very much for telling me. What about the other people? We have some internet problem today. I hope that you could follow me. What about the students that are in Tehran? Do you have also long delay getting my slides, or you could follow the slides? No comment?
شما بچه Actually, I'm not in Tehran, but I also have delay in the cursor, and sometimes it's not clear in black and white pictures, like page 61. It was not somehow trackable.
So perfect. Thank you for telling me. This kind of long solution that we are working is usually not tractable in a class. Even if we are just writing everything on the blackboard and you are looking at it, you cannot digest all the parts in the classroom. I'm just giving you the flow chart, how this is working. And you should do it yourself. You should practice it yourself. And we give you the practice in the examples, in the assignments, and also in the project. Of course, I never go for a 6 degree of freedom, although the kinematic roboticists are very, very fan of 6 degree of freedom robot. But since I am not a roboticist, a kinematic man, and I'm more a control man, usually I just go for 3 or 4 degree of freedom. So your examples and your basically your project is only 3 or 4 parameter. Of course, both of them are quite valuable and very interesting in terms of application. Any other questions? If you don't have any question, I just go through the next, the last part of inverse kinematic problem. I don't go through the examples. I just give the idea to you and stop the class here, and we'll give the final part of the course at the last session that we have in the 14th century. And our next class will be in 15th century, and this is a matter of interesting happening or occurrence that we have in here. It is very, very, very interesting that if we use the screw, a successive screw, we have not saying much simpler, but we have simpler solution for inverse kinematic. And this comes from the idea that a successive screw, for a successive screw, this is a theorem proven in the screw algebra, that if you have a number of successive screw represented by homogeneous transformation, if you have a position given at the reference frame, and then you put it here when the angles are all 0. You put, you map it through the successive screw, you can find the position of P over there. So what we do in successive screw is very similar to what we have done for P-pair solution. In P-pair solution, we distinguish between the wrist point P or point W to the end effector point Q. And then the orientation of the wrist was basically somehow distinguished or get independent in the equation. So we isolated these two. We do the same thing with the screw, but the only difference is it is much simpler to write this equation for any position, not only for position, but also for orientation. And we do that. And this makes the life much easier rather than having all the matrices multiplied to each other without having some sort of insight. Here what we do, we use this type of manipulation. Usually we find a position P which is the smallest number of screw coordinate could implement in that. So we usually use the first 3 screws as we did in the previous question, or depending on the problem, maybe the only first 4 screws to find a position which is related to that 4 screw. And then instead of solving that, usually we use the inverse of one of the problem, one of the screw angles, or for one of the screw homogeneous transformation to the left-hand side. We use this part to just distinguish between the parameter θ1 to the other one. And if this A2 to AI, if the AI is not very much, if it is only 2 or 3 screw, then we can solve this equation by some sort of intuition and some manipulation as we did for the peer-pair solution. This is usually works out well, and also not only for the position we can show that in terms of the orientation, the rotation matrices, not the whole transformation, just the rotation matrices can be used as well here. R1 to R6, W0 gives you the W. The orientation matrix, we have an orientation matrix UVW. You see the final orientation matrix. We can consider that orientation matrix also as 3 vectors, and we can use the magic of screw mapping as we taught here. Any vector in reference frame multiplied by this gives you the vector in the final prime or target prime. This vector could be the orientation vector, the U or V or W, the component of the orientation vectors, U, V, W here. And if this, instead of having this 6, if we have some intersecting point like a peer-pair, if you have only 3 orientation here, this solution would be much easier. And then also we can use one of them, inverse of them to the other side to make it much easier. And usually to find this, as I mentioned, we usually use the 3 components to the other side and 3 component to the other side to make the life much easier. By this means that the solution or the method of thinking is the same as we did the peer-pair. You should work on this problem quite extensively. You should look at the book, the details, and also the slide, what we did here. But here, instead of using the Denovitt-Hartenberg transformation, we use the screw transformation. And if you have done the forward kinematic in a successive screw method, which was much easier, do you remember that? Then here again we can find the inverse kinematic with the successive screw component, which will be I don't say much simpler in terms of 10 times simpler, but it is more readable and tractable in terms of this kind of solution. We have 2 examples here. Again, 2 6-degree of freedom example here. One of them is the 6-degree of freedom elbow manipulator, and the other one is the Stanford arm, which has a P manipulator here. I don't go through the details of both of them here because there are so many equations. I will leave it for the next session. But I would like to you, before going to the screw axis, please completely follow the Fanuc example and how we have done that, that you can easily follow what we are doing in the next session on the successive screw. So there is no much difference in terms of the method that we are using. The only difference is instead of using basically this Denovitt-Hartenberg transformation, what we are doing here, we are using the screw axis transformation and also the rotation matrix part of them for finding the orientations. I will basically stop here and give the 2 examples hopefully for the next session before going through rather long holidays in the next year. If there is any question or comment, please.
Excuse me, should the can I go ahead?
Yes.
Should the references be intersecting here as well in the screw method for the orientation part?
I still didn't get your voice quite easily. What is interesting?
I'm saying the references in the wrist should be intersecting like the previous method or no?
If it is, yeah, of course, if it is intersecting, you have the separation. But as we see in here, these are not intersecting. And we still can have the solution. It is not, and as I mentioned, yeah, this is very good question, very good question. Thank you, Zahra. Usually you ask some question that I have not fully ever elaborated in the class. You know, when we have the Pieper theorem, or if we have the three intersecting point, the solution becomes much more easier to find. This doesn't mean that if we don't have intersecting joints, we cannot find the solution.
Right.
And right now, when I was a student, going back to 20 years ago or something like that, or maybe more than that, yeah, it was 30 years ago, yes, in 1991, there was only the Pieper solution available. But now there are the most general 6 degree of freedom robot. If it is 6R manipulator, we have all rotary joint. There is the inverse kinematic is fully well known and understood. It is difficult. It is much more difficult than what we presented here, but it is fully developed. In screw coordinate, is the same thing will happen. If we have intersecting point, so we can separate the problem to two problems from each other, and we can just solve one by one. But if they are not intersecting, or we have R and P, you know, sometimes we have not only R, we have a few R parameters, a few P parameters. Then this intersecting is also not that simpler, making it simpler, but make it somehow more difficult in terms of the understanding. Again, what we have to do is, as I mentioned here, what we have to do is find the simplest way or the simplest number of rotation that you can find a position at the reference frame to a position at the target frame, or find the orientation of the reference frame to an orientation of the target frame. If they are intersecting, it is much easier. But if it is not intersecting, maybe this problem becomes much more difficult. We have 4 parameters over there, but only 2 parameters remaining in this part. We have more difficult time to find the positioning to solve the positioning part of the inverse kinematic, but much simpler time to find the orientation part to that. But usually there are, at this point when we are talking at this time in year 2021, almost none of the problem are unsolved, and we have usually many manipulators being worked on and the inverse kinematic being found quite well.
Thank you, sir.
If you need some more research program or research material being seen in here, let me bring you some material here, if you don't mind. If you look good, go to the Tesai book. I hope this will be open. And if you go at the very end, of course not the references, long. Yeah. Two methods given here. One on rod solution for a 6-degree of freedom robot. This is good to read. You have the Sylvester elimination method. All of these methods are good for inverse kinematic. And more than that, which is quite interesting, the continuation method. I hope that I can find the continuation method here. Yeah. This continuation method is one typical way to put the inverse kinematic problem into polynomial equation and find the solution for that. And these are very, very interesting issues that you can find, of course, quite advanced method that you can find in here. Please go, if you would like to read more, you can go to these 4 appendices, 3 appendices, and the continuation method. Read the continuation method if you are working on the inverse kinematic problem. Thank you very much. If there is any other question, please. If there is no question, we will have our last session in the year, hopefully on Tuesday, and I will complete the chapter 3 by that. Please be aware that your assignment number 2 and also your project part 1 will be uploaded today on the site, and you can get them and work on them for the next 3 weeks. Thank you very much and goodbye.